can join extra session if you want today. Today, Jesus, tomorrow. Today also you can join this in the exercise sessions, but tomorrow we have extra one. What do we do next week? A tricky question? Yeah, we have vacation next week, right? So don't come to university because there's no teaching. Good. Yeah, it's cool, but so let's go to. So we talk about state machines. We talk a bit about continuous modeling. Then really you have to know a bit about control engineering, but as a software you will often end up modeling and implementing discrete systems. So state machines are very handy. In real life scenarios, most systems are hybrid. So meaning that if the red ones actually model kind of continuous part, and this is the discrete with jumps, most systems will have kind of exhibit a hybrid behavior. So there will be, and most often what you will see is that they will actually have like continuous behavior, but they will change from state to state. This is very typical. Like if you consider a drone, it can actually fly, and if you wanted to make like a trick, in this one I think it can do a flip. What is actually going to happen is that it goes into like different modes, so it's going to actually go from the impulse to drift and recovery afterwards. And for each of those states, it's actually going to run different continuous paths. So it will actually try to execute different control depending on the state it is. And the state actually will be modeled using state machine, and the other one will be actually modeled using differential equations most of the time. So typically in these cases you will have again kind of an actor model with state machines. So you have actors that take inputs, generate outputs, but each state actually is going to, so it's not the block that's going to execute a continuous part. In this case, actually the states are going to execute kind of the implementation of the different continuous part, and you will control the change. So for example, if you take the thermostat, you can have a basic system, discrete system, but you also can have a more sophisticated system, which is a hybrid one, and you can say that actually you have heat on and heat off systems, and there's a temperature, there's an input to your actor, and you can model that as a hybrid system, so you can have the state machines, but each of the actions, so the cooling and heating states, will implement actually a more sophisticated system. In this example, it's continuous time output, but it's going to be heating or cooling, right? And actually in this case, it's a heating, and there's lack actually of heating in the cooling state, so we have passive cooling. But of course, you could have a more interesting execution of the states and the heating or cooling, so it doesn't need to be linear or just on-off state. And there are different types of hybrid systems. What is typical is that there is a time that comes into picture. So if the system has an input which is temperature and an output which is the heating on-off, what is typically you will see is that so this is actually another example of implementing hysteresis. So we actually had the system where we had actually the heat on state with on going 18 and actually the other one going before. So there's no chance actually you can be in two states at the same time. Here's another example of a state machine with cooling and heating, where you can see the temperature actually the change here is at the same kind of temperature point, which is 20 degrees. Hopefully you can see that. So there's a transition going from cooling to heating when the temperature is less or equal to 20, and there's change, so there's a transition going from heating to cooling where the temperature is greater or equal to 20. That would be kind of flawed in itself if there was nothing else, but there's another guard, and that's a timer. So we actually have a timer that originally is set to TC, and then if the timer is greater than TC, actually it allows you to change and you reset the timer. And actually when you are in the state, you increase the counter, so you actually count up, and again, if after a while the temperature is higher, you will change. So here actually the hysteresis is not on temperature based, but is time based. Right? So here actually we have hysteresis which is 4 degrees Celsius, and you will also actually exhibit the same. So there will be actually temperature, this is heat on. Okay, my handwriting is worse than the doctor, so don't worry. But here the difference is actually time. So we don't know actually what is the temperature, that's based on the physics, but we know that there is a gap which is TH and TC. So from cooling to heating is TC, and from heating to cooling is TH. Every time you change the state, you reset the counter, and when you are inside the counter, you actually increase when you start counting up. Right? So the system is not going to oscillate, it's just going to change state after some time. And of course the guy doing the design has to make sure the time actually reflects the kind of model of a system. Why? Because any system dealing with temperature is slow. It's not easy to heat up a room in 5 seconds. It's mostly probably is going to take 15 minutes. And if it's a slow heating, it's going to take hours. So that's the unfortunate thing about floor heating. And that's why you should never switch off floor heating, because it will take hours to turn it on and get the temperature in the room. So anyway, so some of the systems of the class can be time automata, where actually, like in this example, the time is part of the model. The other one is supervisory controller, when actually the supervisor kind of controls the other part and controls how the inputs are handled. This is also very typical in control systems. So if we consider an example, if you consider a powertrain, so an engine, most of the engines are software controlled, and typically you will have at different states. So typically there's a startup where you control the system a bit differently because the engine is kind of not prepared for kind of running, so you have to typically give like extra oxygen and kind of control that a bit differently. Then you have a normal operation, then we use a feedback controller, and then you have a power where actually you want to get extra acceleration, and you get extra power is going to change actually the controlling again. And you also can end up with failure modes where, for example, sensor, the one that actually measures something, actually gets faulty. And typically, depending on the situation, because you might think that one of the best things is to kind of shut down the engine to protect the engine, but often it's not the case, especially if they're driving on the highway. So what's going to happen on the highway when the engine has a failure? And assuming the skid run, it will just run slow. You will get this funny red icon on the dashboard saying that you should go to service, and you can drive whatever 20 kilometers per hour to leave the highway. Right? So then you know your engine is in a failure mode. It discovered something potentially dangerous and you should do something. So So save mode doesn't mean stop, especially if you're on the highway. That's why actually considering fairness is dangerous, but they should be considered. So that's very important. Especially like if you are in a plane and the engine discovers that there's something wrong. You don't really want in a plane the engine to turn off, right? So that's probably a different case. And there are also other scenarios. I think one of the very interesting I learned is that there's like in ventilation there's something called fire mode. So in ventilation, like we have here in the buildings, we control the level of CO2 typically. Okay, maybe Alcyon is a bad example because we do that by opening windows. In normal buildings, there's ventilation, air conditioning, and you actually control the level of CO2 by running fans. And when the ventilation system discovers that the engine is too hot, it will alarm the building management system and typically will shut down to protect itself. However, in the case of fire, it doesn't matter what condition and state is the fan, it should continue blowing air. This is very interesting for different reasons. So in normal operations, when the temperature exceeds limits, you should shut down the system. However, in a fire case or event, you are not sensitive to temperatures. So you should kind of run to death. So actually, designing those systems is very interesting. The other thing I would like to mention, so besides modeling behavior, we also need to model computations. That's a different story, right? So we learned about processors, interrupts, how we actually run, the ALU, how we control the flow of the programs. We learned about processes, threads, message passing, so the multitasking part. We learned a bit about actually how to model that, but on top of that, we have other modes of computations, like data flow, time triggers, synchronous, and so on. So typically on the higher level of abstractions, we kind of don't spend time, or we kind of try to abstract the threads and processes, and we try to focus on the higher level models. Typically we consider components and communication protocols. So you typically kind of think about what is actually the active object, how do I run the components of my system, and how do they communicate. And there are different ways of dealing with that. So typical way is to think about the components and the communication in terms of graphs. So you typically model the system as a process networks when components actually do the computations, and there are vertices, and then you have the communication links that are actually, I think it's done. And they're actually modeling the links between them actually model the communication. You can also do that opposite, depending what is your focus. So there are different types of models based on graphs that can really model that. So the task graphs may include following extensions. So as I mentioned, you can really model things differently, and depending on your model, you can actually then use that model, because what would be the reason for doing those models? That's because you want to reason and analyze them afterwards. So you actually really want to have the models be able to reason in terms of the system behavior, and then map those to something you can execute on the system. So again, no AI, no LLMs, just math, okay? So math is everywhere. So one of the informations you could add is timing information. So when the tasks actually arrive, what are the deadline periods, and so on. The different types of relation between computations, like constraints and dependencies between them, so exclusive access to resources. If there are any, like, for example, printer or data pool, database that you want to access, and how you actually want to manage those, like periodic schedules, This is if you go again to signal processing, which is kind of more into control part. Yeah, you actually want to see that, especially if you go into the frequency domains. So that's why actually digital signal processing is mentioned here. And then hierarchical graph nodes, where actually you have typically a kind of graphs in graphs. So when your system is more complex, and typically you cannot really model everything using like one graph notation. So similarly, you can actually model also communication. So when you think about communication, it doesn't have to be like I send a packet from one thing to another. You try to abstract that. If you're on the same processor, on the same system, the same node, you can consider shared memory because this is like the easiest one. The other one is message passing. You know, so we don't explicitly say we use tasks, processes, and pipes. We try to kind of abstract that, and we try to consider really on the important aspects of the application, how to exchange information, and then how they could be realized. Yeah. When it comes to actually kind of really implement those, and then how to map that, the different behaviors and the computations within the components. Yeah, we can do that differently. So we of course can run differential equations that we'll talk about again. Final state machines that are kind of based on the final states and inputs, outputs, and so on. But we also have data flows and von Neumann models. So there are different kind of ways you could kind of model the computations within the components themselves. That's what we talk about. So one of the common is communicating final state machines, state charts that you know. So besides actually modeling behavioral system, you can also model the kind of execution, and state charts can be used for that as well. So typically those assume implicitly shared memory. So the state machines actually don't communicate with each other over a network, but they actually exchange data using shared memory. So the actions and the information actually are going to be variables that are stored locally. As mentioned earlier, this is 1987. This model is kind of involved. It looks simple, but it's not, especially when you go to systems like here where you have a parallel state machine. So those states, so first of all, it's hierarchical. You have on and off states. This is, the on is refined into actually a state which true, so this is actually parallel, with line monitoring and key monitoring running in parallel. And these things can get really involved, especially when you have state machines, so there will be another one that communicates with this one, because there is like key on, key off, and so on. This can really get involved, and sometimes it's really difficult to reason about them. There are also, I think, like paradoxes, where you can have two state machines triggering itself at the same time, which is quite difficult. The other types of kind of computations or models for modeling computations within the components are data flow models. So this is typically expressed in terms of function block diagrams. We have an example here. This is typically what people actually use because it's close to our intuition. So most of the control systems are actually modeled using data flow diagrams where you have blocks that perform functions, and the arrows actually mean flow of data. And there are models, there are many models actually that model that, like Petri nets, because what is special here is the flows. They kind of can trigger execution of the function blocks, so they are responsible for firing the executions. And you can also specify actually the tokens. So actually every time, what number of tokens is needed to actually trigger the execution of a block, and what is the output, so how many tokens actually a block can generate. Typically is 1 to 1, but this can actually be also different. So this is the modeling of those executions can be involved, but that's typically what humans can cope well, and that is contrary to UML. I mentioned the second time. UML actually has been seen as kind of remedy to the problem of designing software systems. However, the original actually model, if you consider, for example, class diagram, is counterintuitive. What do we model using links in class diagrams? I mean, if you show to any normal person, normal meaning not software engineer, and if you show a class diagram, then no one will understand it. Everybody will understand this model. If you show a class diagram, they will not get it. Why? What is used to express links? So if I do, so what do we have actually there? Customer list, customer queue. So let's say this is customer list. We have customer queue. And let's say there's customer. What is this mean? It's obvious, right? It's only software engineers can understand that this is dependency. Flow normally means flow of data. Everybody understands that. This is how river flows. What do you get when river flows? It moves mass, right? For some reason, computer scientists believes arrows have different meanings. So, and that's probably one, there's a big difference between being computer scientist and software engineer. So please remember that. We are not computer scientists. We are software engineer. And if you go to guys like mechatronics and control engineers, they will have no understanding of software models in terms of UML. It's foreign kind of model. That's why that's one of the reasons you will more or less nowhere see UML diagrams in industry. This has been heavily promoted 90s and beginning of 2000s, and honestly, I never seen that myself. You will see typically some of those diagrams to model like use cases, something that is hard to capture. Otherwise, there's very little value in modeling graphically textual software artifacts. I mean, you don't rise level of abstraction when you show a class diagram. It's just illustration of the code. That's it. So that's actually in contrast to the data flow models. They actually show more naturally how data flows. Unfortunately, of course, you cannot see what is relation between some of the boxes, right? Probably there's a difference, you know, they use coloring. There are blue ones, yellow ones, and green ones. So maybe there are different classes. So in terms of UML, you could use class diagram to show that, right? They decided to use coloring. So there are different ways of doing things. Anyway, today we are going to talk about MATLAB. So MathWorks. This is kind of a de facto standard tools in the industry for model-based design. It's actually also a domain-specific modeling. This actually when you consider Simulink at least. So MATLAB typically comes together with Simulink. If you go to industry, I don't know any company that uses MATLAB alone. So you have MATLAB, Simulink, plus a lot of extra packages. And they actually use models and they are data flow models. That's why actually I mentioned them. So you will see, and actually they model continuous behavior most of the time, but because the model has been extended, nowadays in Simulink you can model any type of behavior. There's an extra package that we're going to use called Stateflow. Actually I have that, so yeah. So anyway, I will just talk about it in a moment. So this comes with a lot of toolboxes. This is all software. What is you should know that for us is free. In industry is horribly expensive. I think one toolbox is around 5,000 euros. I don't remember. It's just astronomical. But industry will buy that anyway. Because it's de facto standard for kind of doing model-based design and simulation. So it's not only for designing and generating code, it's also for actually doing simulations. So there's a Simulink. So this is the add-on that kind of is de facto standard. And it specializes, as I mentioned, modeling the continuous part, but you can also do discrete and hybrid systems. So that was added. So you can actually do kind of any model, any type of system over there. And remember, we are engineers, so we model the stuff and we use it to generate the code, right? So what we do here, we don't model a real physical system. We actually try to model something we can use afterwards. So if, of course, if you want to model the plant, you will try to model the physical model as close as possible. But typically we focus on modeling the controller that will result in implementation on the embedded platform. So the Stateflow is another important add-on. It kind of comes with Simulink, but you know, Matworks has a very interesting business model, so they want to create as many add-ons and packages as possible, right? So you can actually do discrete control in Simulink, but if you want to do hierarchical state machines or state charts, you need Stateflow. So you have to pay extra to get another add-on to do state machines. And that's yet another symbol for that. So we can do final state machines, and yeah, it really implements the state charts model in MATLAB Simulink. What is interesting is that from there you can generate code. So if you model your system in MATLAB Simulink and Stateflow, you can use embedded coder, and this allows you to generate C++ code. That's what we tried today. There's also HDL coder, so believe it or not, it also can generate code for the VHDL code for the FPGAs, and you can program the programmable logic. And that was probably the revelation of 2000s, where we actually got a tool chain that was able to generate the implementation from the models end to end. Probably is not the most efficient, but it works. And actually, what is actually interesting is that if you go and develop software for functional safety, so kind of fault-tolerant systems, systems that need to be safe by default, using actually MATLAB, Simulink, and Stateflow can guarantee that. So actually that toolchain can be certified. I mean, it is certified, but you have to show that you use it correctly in the company. And you can do like functional safety systems just by doing models. You don't really need to implement code. Of course, there will be middleware. You will need an operating system, but you don't really need to be concerned with the application code. You can just buy MATLAB Simulink, certify software, and you can generate the rest from the models. So, yes? So, in a few moments, you will need actually MATLAB Simulink. Hopefully you have that. And we are moving to 109. Questions? I actually finished on time. Geez. So, we are going to use MATLAB Simulink and Stateflow. And we are going to generate code, so you also need MATLAB coder, embedded coder, and Simulink coder. And don't ask me why you need all of 3 coders. That's again MATLAB business model. So. But for you it's free. So you should use it now because it's not going to be so free after you finish your education. Good. So see you in one line.